Download this code from codegive.com, link in the description below. Dealing with blocking sockets when the buffer wants more than available, a comprehensive tutorial. Blocking sockets are the simplest type of sockets to work with, but they can present challenges when reading data. The core issue arises when you attempt to read a specific number of bytes from a blocking socket into a buffer, but the socket doesn't have enough data available at that moment to satisfy the requested read size. This tutorial will delve into the complexities of this situation, providing clear explanations, code examples in Python, a commonly used language for networking, and best practices for robust handling. Understanding blocking sockets. Blocking behavior. When a blocking socket's recv, or similar read function, is called, the program's execution halts, blocks, until one of the following occurs. Data is received from the socket. The connection is closed by the remote peer. An error occurs, example connection reset. Simplicity. The blocking nature makes code straightforward to write initially. You expect a recv call to eventually return some data, even if it's less than you requested. The challenge is handling that less than requested scenario gracefully. Drawbacks. Blocking sockets are inherently single-threaded in their blocking behavior. If your application needs to handle multiple connections concurrently, you'll typically need to employ techniques like threading, multiprocessing, or asynchronous programming, asyncio, to avoid blocking the entire application. The problem: reading more than is available. Let's say you want to read 1024 bytes into a buffer. In this simplified example, the server listens for a connection, accepts it, and then tries to read 1024 bytes using con.recv, 1024. What happens if the client sends only 500 bytes before pausing or closing the connection? The recv function will still return, but it will return only the 500 bytes that were available at that moment. It does not wait indefinitely for the remaining 524 bytes. Scenarios and consequences. 1. Short reads. If you were expecting precisely 1024 bytes for a particular message format, a short read will cause your parsing logic to fail. You'll have an incomplete message, and attempting to process it might lead to errors or unexpected behavior. 2. Connection closure. If the client closes the connection before sending all 1024 bytes, recv will return an empty byte string, b. This signals that the connection has been closed by the peer. Failing to check for an empty byte string leads to errors. 3. Partial data handling. You might be writing a function that assumes a fixed size message. With short reads, it will only process part of the expected data, potentially leaving the rest unhandled. Solutions and best practices. The core principle is, never assume recv will return the number of bytes you requested. Always handle the possibility of short reads and connection closures. Here are several approaches. 1. Read until a delimiter. This is a common approach for text-based protocols, example HTTP, SMTP, where messages are separated by a delimiter, example new line character \n, \r\n. Chunking. Read data in chunks, example 4096 bytes, to avoid blocking indefinitely. Adjust the chunk size based on your application's needs. Larger chunks might improve efficiency, but smaller chunks can improve responsiveness in some cases. Buffering. Accumulate the received data in a buffer until you find the delimiter. Delimiter search. Use the in operator, or find, method, to check if the delimiter is present in the buffer. Splitting. Split the buffer at the delimiter to extract the complete message and the remaining data, if any. Asterisk connection closure handling asterisk check for an empty chunk to detect connection closures. Decide how to handle a partial message in this scenario, example log a warning, raise an exception, attempt to process what's available. 2. Read a fixed length header first. This approach is useful when you have messages of varying lengths, but you can include a fixed size header that specifies the total message length. Asterisk header structure asterisk the header usually contains the total message length, and sometimes other metadata like message type or version. Asterisk struct module asterisk the struct module is crucial for packing and unpacking data into specific binary formats. Struct.pack converts data into a byte string, and struct.unpack converts a byte string back into data. Choose a suitable format specifier, example I for a big-endian unsigned integer, that corresponds to the data type of the message length. Network byte order is generally recommended for consistency across different architectures. Asterisk reading the header asterisk first, read the fixed size header to determine the total message length. You should accumulate the header data in a loop, like the receiving message data loop. Handle early connection closures. Asterisk reading the message body asterisk once you know the message length, read the remaining bytes of the message. Again, use a loop to handle potential short reads, ensuring you read exactly the number of bytes specified in the header. Asterisk error handling asterisk add error handling in case the message is corrupted or the connection drops unexpectedly. Asterisk data type choice asterisk use appropriate data types in the header. If your message length can exceed the maximum value of a 2-byte integer, use a 4-byte integer, or even an 8-byte integer for extremely large messages. Client-side example, for the fixed length header. Asterisk sendle, asterisk the sendle method attempts to send all the data. While it retries internally if the socket buffer is full, it's still possible for it to raise an exception if the connection is broken. Asterisk struct.pack, asterisk the client must use the same format specifier, example I, as the server when packing the message length into the header. 3. Using a separate thread or process. For long-running connections that are blocking, it may be necessary to move the code that reads from a blocking socket into a separate thread or process so that the main thread is not blocked. This enables the application to remain responsive. Using a thread has the advantage of being faster as there is less overhead. Using a process enables the application to handle problems in a less catastrophic way as an issue in the networking code will not crash the application. In both examples, the network connection is established in the main thread, but the network handling is moved to a separate thread or process. Asterisk main thread responsiveness, the main thread is no longer blocked by the recv calls in the handle_connection or process connection function. It can process other tasks. Asterisk resource considerations, using a thread is generally lighter than a process. However, due to the global interpreter lock in Python, GIL, threads cannot truly run in parallel and may not be suitable for some CPU-intensive applications. If you need to use the CPU a lot, use processes. 4. Select or poll, non-blocking with event loops. This advanced technique allows you to monitor multiple sockets simultaneously and only read from a socket when data is available. While it adds complexity, it's the foundation for high-performance network applications that handle many concurrent connections without threads. Asterisk non-blocking sockets asterisk set blocking, false, is crucial. This makes recv return immediately, even if no data is available, returning an error that you need to catch. It also does the same for except. Asterisk select.select, asterisk this function, or select.poll, which is better for a large number of connections, monitors a list of sockets for readability, data available, readability, ready to send data, and exceptional conditions, errors. Asterisk event loop asterisk the while loop continuously checks for socket events. Asterisk handling events asterisk when a socket becomes readable, you can call recv, without blocking. If it's the server socket, it means there's an incoming connection to accept. Asterisk buffering, again you'll still likely need to buffer data if you're reading messages with delimiters or fixed length headers. Asterisk error handling asterisk handle errors like blocking I/O error, which can occur when reading from a non-blocking socket with no data, and connection reset error, connection closed by the peer. Key considerations. Asterisk protocol design asterisk the simpler your protocol, example using a fixed size message format, the easier it will be to handle partial reads. Complex protocols may require more sophisticated buffering and error handling. Asterisk buffering strategy asterisk carefully consider how much data you need to buffer and how long you should keep it in memory. Too much buffering can lead to memory issues, while too little buffering can lead to performance problems. Asterisk timeout values asterisk consider using timeouts, example socket.setAmout, to prevent your application from blocking indefinitely if a connection becomes unresponsive. However, timeouts should be used carefully, as they can also mask legitimate network delays. Asterisk error handling asterisk robust error handling is essential. Handle connection closures, network errors, and invalid data gracefully. Logging errors is critical for debugging and troubleshooting. Asterisk platform dependencies asterisk be aware that some socket behaviors and error codes can vary slightly between different operating systems, Windows, Linux, Mac OS. Choosing the right approach. Asterisk delimiter based asterisk simple and suitable for text-based protocols. Asterisk fixed length header asterisk good for messages of varying lengths where you need to know the total length upfront. Asterisk thread/processes asterisk useful for long-running, blocking connections where you don't want to block the main thread. Simple to implement, but may be resource-intensive for many concurrent connections. Use threads if the networking isn't CPU-bound. Use processes if the networking is CPU-bound or you require robustness. Asterisk select/poll asterisk the most complex option, but provides the highest performance and scalability for handling a large number of concurrent connections efficiently. Use this for high-performance servers that require many connections. In summary, handling short reads with blocking sockets is a fundamental aspect of network programming. By carefully considering the possible scenarios and employing the appropriate buffering and error handling techniques, you can write robust and reliable network applications. Always be prepared for recv, to return less data than you requested and handle connection closures gracefully. Choose the right approach depending on the protocol you're using and the concurrency requirements of your application.